Today we will start a new chapter, and in this chapter we will develop numerical techniques to get more accurate integration, numerical integration. The main objectives of this chapter is to recognize that Richardson extrapolation may be used to provide more accurate integral estimates by combining just two less accurate estimates. So we will see that if we decide, for example, to use a certain method, this extrapolation can be done based on any method. So you can, for example, choose the trapezoidal rule to compute integral. You can use different step sizes. And of course, higher the step size, higher is the accuracy. The idea is that Richardson extrapolation will allow you to estimate a new value of the integral that is more accurate than the two estimates you done using two different step sizes, of course, using the same method. So we will see how we can obtain this. Second, we will look over another method, which is Gauss quadrature, which provides more accurate integral estimates by optimizing the choice of points. So we will see how even with just a linear interpolation, we can give an exact integral for higher order functions. You can do an estimate for a function of degree 2 or 3 by just using a linear function, which is very good, and we'll see how to do it by proper selection of points. So this is, in summary, the main objectives of this chapter. To start with, we will give an example where we can use Richardson extrapolation. So in case you have a static beam that is subjected to a load, you can show that, if you have already taken the statics course, you can show that the displacement of the beam is related to the load applied through the following relation. Okay, and then we can determine by integration we can find the displacement of the beam. So now let us see in general if we solve for this displacement for this beam deflection using let's say a certain step size h1, which is 0.1, we will obtain the following blue curve. Now if we do another step size h2, we will get a more accurate result by selecting h2 smaller than h1. Now what we will do then, we will combine these two solutions of integral to get a much more accurate one. We will see how. Okay, so by just combining these two, you can end up with a much more accurate solution. So you can see in red the true error induced by combining the two solutions compared to the true error for using just H1 and the true error using just H2. And as you can see, the error when combining both will be much lower. It is nearly zero. So even you cannot see this error because it's very small compared to a larger error for H2 and much larger error for H1. So we will see how to obtain this small error by combining these two solutions. And of course, our applications are the same applications that we have seen in previous chapter, because integration can be used to calculation of volume, to calculation of area, to the prediction of integral of complex function, etc. So now, let us start with Richardson extrapolation, also called Romberg integration. And this extrapolation, as I told you before, can be applied to any technique that we developed in the previous chapter. In the previous chapter, we have considered trapezoidal integration, we have considered the Simpson's 1/3 integration, Simpson's 3/8 integration. All of these methods can be used with Richardson extrapolation. Just the condition is once I choose the method to stick to it. So I cannot get, for example, I1 using trapezoidal integration, then use I2 using Richardson 1/3. No. If I want to use Richardson extrapolation, I will stick to the same method because the error should be of the same form. If I change methods, the form of error will change, and what I'm doing will not apply. Okay? So Richardson extrapolation will combine two numerical integral estimates to obtain a third, more accurate estimate. We will demonstrate how. So first, let us say we are calculating the integral of a function between a and b of fx dx. And we know that the exact value of the integral, let's say, can be computed. Or if we don't know it, we will just set it to be equal to I. Now, to get an approximation of this I, let us say we are using the trapezoidal integration. So depending on the number of segments, h will vary. If we just take one segment, h will be equal to b minus a. If we take two segments, it will be b minus a over 2. And larger is the number of segments, lower will be h. And we can say that we will obtain an error due to truncation, because you are just considering that your function is approximated by a linear profile, so you are neglecting all other terms. Now, let us look at the following example. We will create two separate integral estimates. So let us say we are working with a certain function, and we selected, we are interested into finding the integral between 1 and 25. So the actual integral will be equal to the area under this blue curve. Now, as a first estimate, I will consider that I will just take two segments. So I will use composite trapezoidal rule with two segments. Then, since n equals to 2, I can determine n1 equals to 2. I can determine the number of, what is the value of the step size. So h1 is just equal to b minus a over n over n1, and here it will be equal to b minus a is equal to 25. So this is 1, this is 25. So 25 minus 1 over 2, which is 24 over 2, it's equal to 12. Okay. Now, if I want to use the composite trapezoidal method, I just apply the rule. If you recall the general rule of composite trapezoidal method, it's equal to the step size, h1 over 2, times, for here, since I am using 3 points, it is fx0 plus, so it's a combination of 3 f's with different coefficients, because the extreme points will just have a coefficient of 1, and all points in between x0 and xn, will have a coefficient of 2. Okay, so here we have fx0 plus 2fx1 plus f of x2 times h1 over 2. We can find an estimate for a first estimate for our integral. Now, a more accurate estimate will be obtained by doubling the number of segments and decreasing, therefore, h by 2. So now if I reduce the step size by 2, I am doubling the number of segments. So now n2 is equal to 4. And then I need 5 points. The first one, so here the step is 6. So the first point will have coordinate x0 equal to 1. The second point will have a coordinate of 7. The third point will have a coordinate of 13. The fourth point will have a coordinate of 19. And the final one will have a coordinate of 25. And then now I am ready to use the same formula, but now with more points. So since I'm using a larger number of segments, so the value of integral obtained by taking a step size h2 is h2 over 2 times fx0 plus 2fx1 plus 2fx2 plus 2fx3 plus fx4. So as usual, the extreme point has coefficients of 1, while all points in between have coefficients of 2. Now, I did two predictions, and I want to try to deduce from these two predictions a much better estimate of the integral. This is why I will try to relate the errors in these two cases. Okay? How to do this? I can say that the value of the integral, which is the exact value, can be written in two ways. I can write it as the approximation using h1 plus the error involved using h1 equals to the integration using h2 plus the error involved when we use a step size of h2. Now, if you remember in chapter 19, we said that if we are using composite trapezoidal method, we'll have that E, the error, the true error, is equal to minus BA over minus B minus A over 12 times H square times F second, and this average of F second was computed in this way, summation of I going from 1 to n of Fci over n. And then we said that the problem is that we don't know exactly where is C. So in each interval, we have a certain position for it, okay? And we don't know where it is exactly. This is why here we cannot exactly know what is the error. So we will come up with a method to have an approximate idea of the error. So we will say, since we are not able to know the location of these points, we will approximate this term here, this term, which is F second average, by the actual average, the normal average over segment BA. So we will compute the average value of F second over between A and B as an estimate for this term. Okay? Because this will allow us to get a certain idea of the error, because we are not able to get the exact value of it. So doing so, we can write now that the error obtained using a step of H1 is equal to minus times B minus A over 12 times H1 squared times F second average, computed as the average value of F second between A and B as estimation. And I can write now for the error obtained when using a step H2 is equal to minus B minus A over 12 times H2 squared times F second average. And now these parameters in the two errors expression, F second average and B minus A over 12, are not changing. Actually, to be very accurate, these terms F second will change. If I want to locate, if I can locate psi for each case, it is possible to know then what is F average. But since we don't know the locations, we will do an approximation and consider that they are equal to the average of F second between A and B. But actually, they are different, because if I change the segments, the locations will change. So there will be a little difference between these two values. But since I cannot assess them, I will take this approximation to get an idea, an approximate idea of the error. It's better than not knowing anything about it, okay? So by doing the small approximation, I can get a certain estimate of my error. Why? Because now, if I just look at my expressions, I can see that if I do the ratio of the error computed when I use a step of H1 over the error when I have a step of H2, will be equal to approximately to H1 square over H2 square. So I was able to find the approximate relation between my errors, function of the steps I used, H1 and H2. And this is very interesting, because if I replace back in my formula here, so here, if I replace back this result, that the error H1 is approximately H1 square over H2 square times error EH2, and I replace it back into my initial formula, which is integral obtained using H1 plus error when using H1 is equal to integral when using H2 plus error when using H2. And now I replace this term here by its value, and now I will get a certain estimate of this error. So before, I didn't have any idea what this error is, but now, when combining the two estimates of my integral, I have an idea approximately what EH2 will be. And this is very good, because now, instead of having a large error, I have a much smaller error, because I did an estimation of the actual error. So now I can say that I can update my integral estimate by saying that my integral estimate is IH2 plus I will replace EH2 by the estimate I got for this error. And I will now get an updated result much more accurate, because at least I accounted for a big part of my error instead of not considering any part of it. And we can show mathematically, and you are not responsible of the demonstration, but just you should know that when doing so, the error, which was of order h square in the trapezoidal rule, so we demonstrated together in last chapter that with trapezoidal rule, the error was of order h square. Here, in this case, when we do this combination, this Richardson method, we end up with an error that is much smaller, and the order now is order 4. So by doing this method, we were able to increase the order of accuracy by 2, which is very good. Okay, so by just combining two solutions of a method of order 2, we were able to increase the order of accuracy by 2. So this is a very powerful statement, because now you will see that I can have much reduced error by doing this procedure, by combining the two estimates of my integrals. And we'll see this in an example. Any question on the derivation? Now, so this is the general expression of I that can be obtained using two estimates of I. Okay, and in a special case where the interval is halved, so if I am doubling the number of segments, then H2 is equal to half H1. I can replace this ratio here by 2 because H1 is 2 H2. So then, in case I am doubling the segments, the relation between IH2 and IH1 will be the following one. I is equal to IH2 plus IH1 minus IH2 over 1 minus 2 squared, which will give me, after expansion, 4 over 3 times integral H2 minus 1 over 3 times integral H1. And from here, I can expect that this method, using this combination, my error will be reduced a lot, because I moved from an error of order h squared to an error of order h to the power 4. And you can see this in this graph again. So now I will go back to this graph to tell you that here, by combining these two and using the formula we adopted in the previous slide, okay, we were able to reduce the error to a big extent. Now let us look at numbers. So we will take again the same example we used in the previous chapter. In this way, you can compare all errors of all methods. So if you remember, yesterday we did an example using the trapezoidal method, and we varied the number of segments. We started by a number of segments equal to 1. This is the trapezoidal rule. And for number of segments larger than 1, it becomes a composite trapezoidal rule. So you have 2. Here now we did it for 2, 3, 4, 5, etc. Now we will just, we are interested into the case of doubling the number of segments, let's say. So here we did times 2. Here we did times 2. And also here we doubled the number of segments. Okay, so now, because we are doubling the number of segments, when combining two integrals, two consecutive integrals, we can then use the developed formula for the case of h1 equals to 2h2. Okay, so first, if we consider first combining I1 and I2, we will get I21. Always the name, the subscript is for the first one. This is the most accurate between the two. So I2 is more accurate than I1. So I21 is obtained by combining I2 and I1. And since the number of segments is doubled, then we can write that I21 is 4 over 3 I2 minus 1 over 3 I1. Okay? And we will perform the same operation between 2 and 4 because 2 is double than 4. So by combining these two, by combining now these two, I can get I42. And again, the name for the first subscript is the more accurate estimate, and the 2 is the least accurate estimate. So you obtain that I42 is also 4 over 3 I4 minus 1 over 3 I2. Okay? And you can combine 4 and 8 to get I84 is 4 over 3 I8 minus 1 over 3 I4. And you can expect that this one will be the most accurate between these three, because here as you proceed, I2 is better than I1, I4 is better than I2, and I8 is a better estimation than I4. So when you combine, this will be the best choice. Now, how your error is decreasing? You know that in the trapezoidal rule, we said that the order of error is h squared. This is why we expected that when doubling the number of segments, so when dividing h by 2, the error will be divided by 4 because the error is proportional to h squared. And therefore, again, approximately, I repeat, not exactly, approximately. Why we approximately? Because we have seen that we have in factor abscons that will affect the result, but we don't know exactly how much it will affect it. Okay? This is why we say approximately, because we also have the effect of abscons that is unknown. So you can see here that nearly, for the first between 1 and 2 here, it was nearly 90. So, and this is nearly 35. So it's not exactly divided by 4 for the reason I told you, because we have the effect of effect. Okay? When going from 2 to 4, we were closer to the decrease by 4 because this is nearly 40, this is nearly 10. And then when going between from 4 to 8, we had nearly 10 to nearly 2.5. So actually the error was approximately divided by 4. Okay, so you can see here that the effect of abscons was reduced when increasing the number of segments, because here for the first step it was nearly just divided by 3. So the effect of abscons was larger when going from 1 to 2. But when going from now 2 to 4, the effect was reduced because now you can find the ratio of, it's nearly now 3.5 as the ratio. And finally, it's nearly 4 as a ratio. So as you increase the number of segments, the dependence on abscons will be reduced. Okay. So now I will repeat my calculation of true relative error with the new values obtained. And I expect that, because we said that using the Richardson extrapolation, we gain 2 orders of accuracy. So instead of having the error being proportional to h squared, it's now proportional to h to the power 4. And therefore, I expect that approximately when I double the number of segments, so when I divide h by 2, my error will be divided by 2 to the power 4, so by 16, which is a very powerful. This is why Richardson extrapolation is a very powerful method. Because here, for example, when you use the first estimate I21, you got 16.6 as percentage of error. Now, if you, by going from I21 to I42, it's equivalent to divide h by 2. Why? Because in I21, you are using you are using I2 and I1, while in I42 you are using I4 and I2. And to go from I2 to I4, you divide the step by you divide the step by 2, and by going from I1 to I2, you divide the step by 2. This is why we say that we can define a virtual h. So the virtual step in I21 will be equal to 2 times the virtual step of H42. So this is why it's reasonable to consider now that according to this, I will obtain now that the error when going from one stage to the other will be divided by 16, because now my error is to the power, is proportional to h to the power 4. So it's of order 4. Okay. And now, as you can see, also here when going from I42 to I84, also I'm nearly dividing the error by 16. From here, the high accuracy of Richardson extrapolation. Any question on this? Yes.
Doctor,
Yes, Hassan, did you understand why it's approximately divided by 16?
يس دكتور، بس لأنه قبل استعملناها constant.
When استعملناها constant? I didn't understand what you mean.
بس لجمعنا two inaccurate solutions
نعم.
اعتبرنا انه الاف دبل برايم بار اعتبرناها constant. So
مظبوط.
بس بدي اتاكد منك.
ايه نحن لانه اعتبرنا اف دبل برايم اوكي مظبوط، نحن اعتبرناها كونستنت تنعمل الاستيميت، صح يا حسن؟ بس actually هي كونستنت شيء؟
لا دكتور.
لا، منشان هيك you will have nearly divided by 4 او by 16 مش exactly، لانه بعد في الeffect of f second that you cannot know how much it is. يعني whatever you do you cannot be sure قد ايه حتنزل 100% but you can approximate it. This is the positive thing here انه at least I don't know 100% the relation between errors, but I can get an approximation of this relation. So I can expect approximately how the error will be reduced by varying the step size.
Yes doctor, I got you.
Now, what about higher order correction? So you can repeat this procedure several times. So first we started by the composite trapezoidal rule of order h squared. We applied Richardson extrapolation. We got new estimates. So this is the first correction. You got after the first correction I21, I42, and I84. But now you can proceed with corrections. You can do a second, a third, a fourth correction. Okay? And more you do corrections, lower will be the higher will be the order of your error, and you are gaining accuracy. And each time you do Richardson extrapolation, you gain 2 order of accuracy. So when you did it the first time, by gaining 2 order of accuracy, you moved from your error, which was of order h squared, to an error of order h to the power 4. This is why we said that you can expect that the error using the virtual step size h21 over the error using the virtual step size h42 is equal to h21 over a42 to the power, the whole term to the power 4. And since, as I told you, by going from I2 to I2 to I1, you divided by from I1 to I2, you divided h by 2, and to go from I2 to I4, you divided h by 2. So you can say that the virtual ratio of h21 over h42 is 1 over 2. Okay, and then you can consider that now the error you obtained will be 1 over 2 to the power 4. Okay, so you reduced you were able to reduce your error by a high amount. هلا هون هن sorry they flipped them. So هون it should be 2 to the power 4. Okay, لأنه h42 is smaller than h21. So if you want to put here 1 over 2, you should switch these. Okay, since h21 is 2 times h42. Okay, why? Because again I will repeat here. You computed I21 based on H2 for I2, based on a certain H for I2 and a certain H for I1. So this is H2, this is H1. Now, when going from 2 to 4, what you did is that you divided H by 2. And when going from, so this was obtained, if you remember here from the table, okay? This is, you got first a number of segments equal to 1, you got I1. Okay, using this was H1. Now to get A2 to get I2, you are using now H2 equal to 0.4. So you to go from I1 to I2, you divided H by 2, and then to go from I2 to I4, you again divided H by 2. So now H used here okay, is h used in 2 over 2. So if you want to keep the names, you can call it here h4. So since when going from I1 to I2 you divided by 2, and when going from I2 to I4 you divided by 2, then you can say that the virtual h21, if I want to define a virtual step, because actually here you don't have one step in I21 because you are combining two values, but you can consider the combined result to have a certain virtual step. And this virtual step will be related to the virtual step of I42, which we will call H42. Okay, so since to go from I2 to I4, we divided the step by 2, and to go from I1 to I2, we divided the step by 2. Then we can say that H21, the virtual step for I21, is equal to 2 times the virtual step for I42. And then again, we can relate the errors obtained in I21 and I42 by using the same procedure, because here, since we are using the same method to compute whenever, so the only condition in Richardson extrapolation is that the error should be of the same form. So you should be consistent with the method used. So here we use trapezoidal rule first, okay, composite trapezoidal rule. Then we combine results obtained from trapezoidal rule. This is why at any stage, the form of error of H21 will be identical to the form of error of H42, okay? And their ratio will be proportional to H21 over H42 to the power 4, approximately. Why? Because now we increased the order from 2 to 4, okay? And here, since H21 over H42 is 2, then you can predict that the error will decrease by 16, because the error in H21 will be 16 times higher than the error obtained with H42. And this is what we actually obtained in the results. So if you go to your results here, you have, when doing the first Richardson extrapolation, you got that your error is of order h to the power 4, and you expected then that your error will be divided by 16, and this is what you got. So when going from here to here, it's nearly over 16, and when going from H42 to I84, it was also divided by 60. Okay. Now, yes.
just to make sure هلا نحن فينا نقارن نقول انه ال I42 هي times ال I21 times 2.
لا مش times 2 الانتجرال you mean؟
Yes, the I.
لا ال I, look, to compare ال I's ما في بيناتهم proportionality ratio.
Yes.
Okay, no. You can compare
ال H.
الerror. بالنسبة لل I, higher is your order of accuracy will be closer to the exact value. بس ما فيك تقول إنه I2 over I1 equal to 2. No, of course no. Okay.
Yes, لأنه حتى إذا شفنا الأرقام ما بيزبطوا.
ما بيزبطوا أكيد، لأنه نحن اللي بنعرفه إنه الerror هي of order h square. بس استعمل trapezoidal rule. ال I, okay, ال I, how you obtain it? ال I you obtain it by using trapezoidal method. يعني هي it's area under the curve. Okay. So it's something completely different. يعني ما في relation بين ال I's, but just you can say that as I am reducing the step, I am reducing the error, and the computation of I is better. And I will have a reduced error. والproportionality ل H square أو H4 هي بالerror مش بال I. Okay.
Yes, thank you, doctor.
Okay. Yes.
مش هيديك